So we'll be starting with tutorial 10 today. These are the problems that we'll be going through. So we've already gone through problem 6.7.1 once in the previous tutorial, but we'll be going through it again just to revisit the concept of approximate central limit theorem. Right, so this is what the problem says. Let K1, K2 be an IID sequence of Poisson random variables, each with expected value E of k equal to 1. Let Wn equal to K1 plus K2 till Kn. Use the improved central limit theorem approximation to estimate P of Wn equal to n. For n is equal to 4, 25, 64, compare the approximation to the exact value of P of Wn equal to n. So let's first revisit the central limit theorem approximation. So it says that let Wn equal to x1 plus x2 plus till xn be the sum of n IID random variables, each with expectation E of x is equal to mu x and variance of x equal to sigma x square. The central limit theorem approximation to the CDF of Wn is f, capital F of Wn of w is nearly equal to psi of w minus n mu x divided by root over n times sigma x square. And this definition is often called the Gaussian approximation of Wn. So in the question, what we have is basically a sum of IID Poisson random variables, and the sum of IID Poisson random variables is also a Poisson random variable. So basically, Wn is a Poisson random variable with mean E of Wn equal to n times E of k, which is equal to n, and basically Wn has a variance equal to n, and the PMF defined as follows. So P of Wn is basically equal to n raised to the power w, e raised to the power minus n divided by w factorial for w equal to 0, 1, 2, and 0 otherwise. So basically using this, what we understand is that the probability that Wn is equal to n is Pwn of n, which is equal to n raised to the power n e to the power minus n divided by n factorial. So basically using the properties of Poisson random variables, we've basically found what the exact value of P of Wn equal to n will be. So now we basically need to evaluate using the central limit theorem. And the reason why we use the central limit theorem is because even though we have the exact formula, it's often pretty difficult to calculate the value of this, because for large values of n, it'll be really tough to evaluate the value of n factorial. So basically using central limit theorem, we have access to the values of psi, and we can just use those to basically get an easy approximation. So the probability that Wn is equal to n will be the probability that Wn is less than equal to some n plus delta and greater than equal to some n minus delta. And delta here is basically a small value, and for the purpose of this solution, we've taken this delta to be basically equal to 0.5. So this is approximately equal to psi of n plus 0.5 minus n divided by root n minus psi of n minus 0.5 minus n divided by root n. So basically psi at a point just ahead of n minus psi at a point just behind of n. So this basically simplifies to give us 2 psi of 1 over 2 root n minus 1. And so in the table at the bottom, what we have are basically the exact and the approximate values. For n equal to 1, the exact value is 0.3679 and approximate value is 0.3829. And as we see, for smaller values of n, there seems to be a small error. But as and when we get to larger values of n, the error becomes even smaller, and the values seem to be approximately equal. So yeah, basically this central limit theorem is often used for large values of n when computation of n factorial and other such values may be difficult. Right, so before we move forward with the questions ahead, let's first revisit the concepts that we learned in section 7.1. And the concepts are basically those of sample mean, And definition 7.1 tells us about the sample mean, and it says that for independent and identically distributed random variables x1, x2 till xn with PDF fx of x, the sample mean of x is the random variable mn of x equal to x1 plus x2 till xn divided by n. So the sample mean is basically the weighted mean, is basically the weighted sum of x1 till xn. And so the theorem 7.1 tells us about the mean and variance of mn of x, and it says that the sample mean mnx has expected value and variance e of mnx is equal to e of x, and variance of mnx is equal to variance of x divided by n. Now these are basically easy to understand. The expected value of mnx will be 1 over n times the expected value of x1 plus x2 plus till xn, and since x1 till xn are IID, we can basically take apart those terms, and that will become 1 over n times e of x1 plus e of x2 till e of xn, and each of these terms is basically equal to e of x. So what we have is basically n times e of x divided by n, so that is the same as the expected value of x. And similarly for variance of mnx, so as we mentioned previously, mnx is the weighted sum of x1 x2 till xn, and so it's basically if we take x1 x2 plus xn to be equal to some random variable w, so mnx is equal to w over n, and basically when we have a constant multiplied by a random variable, and we're trying to evaluate the variance, then we have the relation that variance of constant times random variable is equal to constant squared times the variance of the original random variable, or basically variance of ay is equal to a square times variance of y. So since mn of x is equal to x1 plus x2 till xn divided by n, or w by n, the variance of mn of x will be equal to the constant squared, which will be 1 over n square times variance of w, or 1 over n square times variance of x1 plus x2 till xn. And again, since x1 till xn are IID, that will basically be equal to variance of x1 plus variance of x2 till variance of xn, and each of these will have the same variance, which is basically variance of x. So the numerator becomes n times variance of x, and the variance of mn of x becomes n times variance of x divided by n square, which is equal to variance of x divided by n. Right. So let's move forward with the next problem, which is problem 7.1.1, and it says x1 x2 till xn is an IID sequence of exponential random variables, each with expected value 5. The first part says what is variance of m9 of x, the variance of the sample mean based on 9 trials. The second part says what is p of x1 greater than 7, the probability that one outcome exceeds 7. And the third part says estimate p of m9 of x greater than 7, the probability that the sample mean of 9 trials exceeds 7. So what we're given is basically n random variables x1, x2 till xn, which are independent and identically distributed, and these are basically exponential random variables, and each of these has an expected value of 5. So first let's revisit what an exponential random variable is. So an exponential random variable with the parameter lambda has the PDF fx of x is equal to lambda times e raised to the power minus lambda x for x greater than 0 and 0 otherwise. And the expected value for this is 1 over lambda, and the variance is 1 over lambda square. So for our problem, we know that the expected value is 5, or 1 over lambda is equal to 5, or lambda is equal to 1 over 5, and thus the variance will be equal to 1 over lambda square, which is equal to 5 squared, which is equal to 25. So for the first part, what we have to find is what is the variance of m9 of x, the variance of the sample mean based on 9 trials. So like we mentioned previously, the variance of mn of x is equal to variance of x divided by n. So basically variance of m9 of x will be equal to the variance of x divided by n, and variance of x would be 25. So the answer for the first part is basically 25 by 9. So I think that's direct enough. So basically, if we evaluate the CDF for the exponential random variable that we have at hand, it will come out to be fx of x is equal to 1 minus e raised to the power minus x by 5. That should be easy enough for you to calculate. So the second part says, what is p of x1 greater than 7? The probability that one outcome exceeds 7. So in the second part, we have to find what is the probability that x1 is greater than equal to 7, and this is basically same as the probability. This is basically same as 1 minus the probability that x1 is less than equal to 7, and probability that x1 is less than equal to 7 basically denotes, we can basically find this out using the CDF of x, and this is basically equal to 1 minus fx of 7, and as I just mentioned, the CDF for this particular type of exponential random variable will come out to be 1 minus e raised to the power minus x by 5. So once again, the solution is direct enough, and we have the probability that x1 is greater than equal to 7 will be equal to 1 minus fx of 7, which will be equal to 1 minus e raised to the power minus 7 by 5, which is equal to e raised to the power minus 7 by 5. Right. So the next part says, estimate probability that m9 of x is greater than 7. The probability that the sample mean of 9 trials exceeds 7. So basically, to approach this, we'll once again revisit the central limit theorem approximation, which says that let wn equal to x1 plus x2 till xn be the sum of n IID random variables, each with ex equal to mu x and variance of x equal to sigma x square. The central limit theorem approximation to the CDF of wn is f of n of w is equal to psi times w minus n times mu x divided by root over n times sigma x square, and this is also called the Gaussian approximation for wn. So what we basically have to find is the probability that m9 of x is greater than 7. So what is m9 of x? It is basically equal to x1 plus x2 plus till x9 divided by 9, and the probability that m9 of x greater than 7 is the same as the probability that 1 minus probability that m9 of x is less than equal to 7, and like I mentioned, m9 of x is nothing but x1 plus x2 till x9 divided by 9. So probability that m9 of x is less than equal to 7 is the same as the probability that x1 plus x2 till x9 divided by 9 is less than equal to 7. And if we take 9 to the other side, basically to the RHS, what we have left is probability that x1 plus x2 till x9 is less than equal to 63. So what basically, to find the probability that m9 of x is greater than 7, we have reduced it to the probability, we have reduced it to the value that 1 minus probability that x1 plus x2 till x9 is less than equal to 63. And now we can basically use the central limit theorem approximation. So the sum of x1 plus x2 till x9 is basically another random variable wn or w9, and basically this value p of x1 plus x2 plus till x9 less than equal to 63 can be replaced by the CDF of wn, which is, or w9, which is the sum of x1 plus x2 till x9. And basically using that formula, what we get is that 1 minus probability that w9 is less than equal to 63 is equal to 1 minus psi of 63 minus n times mu x divided by root 9 times sigma x square. And mu x we know was 5, and sigma x square we knew was 25. So replacing these values, we'll get basically 1 minus psi of 6 by 5. Right, so now we'll be moving forward with the next problem, which is problem 7.1.2. And the question says x1, x2 till xn are independent uniform random variables, all with expected value mu x equal to 7 and variance of x is equal to 3. And the first part says what is the PDF of x1. The second part says what is the variance of m16 of x the variance of the sample mean based on 16 trials. And the third part says what is the probability that x1 is greater than 9, the probability that one outcome exceeds 9. And the fourth part says would you expect probability of m16 of x greater than 9 to be bigger or smaller than p of x1 greater than 9. To check your intuition, use the central limit theorem to estimate the probability that m16 of x is greater than 9. So what we're given are basically x1, x2 till xn, which are basically n independent uniform random variables, each with expected value mu x equal to 7 and variance of x equal to 3. And in the first part, what we have to find is basically the PDF of x1. So first, let's revisit what a uniform random variable is. And a uniform random variable with the parameters a, b, where a is less than b, has the PDF fx of x is equal to 1 over b minus a for x greater than a and x less than b. And we also have the graph of fx of x over here, and the expected value e of x is equal to a plus b by 2, and the variance of x is equal to b minus a whole square by 2. So basically fx of x is a rectangle from a to b, and basically a plus b by 2, which is the center point of the rectangle, is our expected value, and the formula for variance of x is b minus a whole square by 2. So what we're given in the question is the value of mu x and the value of variance of x, and we have to find the PDF of x1. And to basically write a formula for the PDF of x1, we have to find the values of a and b. So we're given e of x and variance of x, and we have to find the values of a and b. So basically x1, x2, xn are independent uniform random variables with mu x equal to 7 and sigma x square equal to 3. So we have the variance of x, which is equal to b minus a whole square by 12, which is equal to sigma x square, which is equal to 3, and a plus b by 2 is equal to 7. So on solving both these equations, we get the values that a is equal to 4 and b is equal to 10. And so now we have to write the PDF of x, which is fx of x is equal to 1 over b minus a for x belonging to the interval a to b and 0 otherwise. So a is 4 and b is 10. So fx of x is equal to 1 over 6 for x belonging to the interval 4 to 10 and 0 otherwise. So in the next part, what we have to find is basically the variance of m16 of x, the variance of the sample mean based on 16 trials. So we basically saw in the definition of sample mean, so the variance of mn of x is simply equal to the variance of x divided by n. So that will be equal to variance of x divided by 16, and the variance of x we know is 3. So this simply is 3 over 16. Right, so the next part says what is the probability that x1 is greater than 9, the probability that one outcome exceeds 9. So we've already found the PDF of x in this part, and fx of x is equal to 1 over 6 for x belonging to the interval 4 to 10 and 0 otherwise. So to basically find the probability that x1 is greater than 9, we can just integrate over the PDF from 9 to infinity. And since the PDF is only 0 in the interval 4 to 10, this will basically become 1 over 6 dx. 1 over 6 is basically fx of x. So fx of x dx integrated from 9 to 10, and this is simply equal to 1 over 6. Right, so let's move forward with the last part of this question. And the D part says that would you expect P of m16 of x greater than 9 to be bigger than P of x1 greater than 9? To check your intuition, use central limit theorem to estimate P of m16x greater than 9. Right, so first let's see what we know about x1 and m16 of x. So about x1 we know that the variance is 3, and about m16x we know that the variance is, we found it out to be equal to 3 by 16, and the mean for both of these will be equal to 7. So basically variance or standard deviation denotes how far apart or how much the curve spreads away from the mean. So since x1 has a larger variance, it will deviate more from the mean, and since m16x has a smaller variance, it will deviate less from the mean, or it will be concentrated more around the mean, whereas x1 will be less concentrated around the mean. So, and the mean for both of these is 7, right? So we have to basically figure out if probability of m16 of x greater than 9 will be smaller than p of x1 greater than 9, or will it be greater. So I wanted to take a minute to think about this, and you could also try drawing some graphs. So basically, since M16X has a lesser variance than X1, I think it's basically safe to say intuitively that M16 of X will have a lesser portion of the curve beyond 9. So when we try to find P of X, M16X greater than 9, we'll be finding the area of the curve, basically area below the curve from 9 to infinity, and so that area for M16X should be less than the area for X1, as M16X is more concentrated around 7, whereas X1 is less concentrated around 7. So basically, since variance of M16 of X is less than the variance of X1, the PDF of M16X should be more concentrated about E of X than PDF of X1, and therefore basically P of M16 of X greater than 9 should be less than P of X1 greater than 9. So basically, this is what we get intuitively. Now we basically need to uh, find out the approximate value of P of M16x greater than 9. We can find this out using the approximate central limit theorem, and by finding this value, we can figure out if our intuition was basically well placed or not. So the probability that M16 of x greater than 9 is the same as the probability is same as 1 minus the probability that M16x is less than equal to 9, and this can be replaced by something like a CDF, right? So M16x is nothing but x1 plus x2 till x16 divided by 16. So basically 1 minus p of M16x less than equal to 9 is the same as 1 minus p of x1 plus x2 till x16 divided by 16 less than equal to 9. So we take 16 to the right hand side and we get 1 minus p of x1 plus x2 till x16 less than equal to 9 into 16, which is equal to 144. So basically applying the central limit theorem of approximation again, this will basically be equal to 1 minus psi of 144 minus 16 times mu x divided by root 16 times sigma x, and mu x we know was 7 and sigma x was 3. So when we replace these values, we'll basically get the value 1 minus psi of 2.66, and this totals to be 0.0039. And basically we found out in the previous part p of x1 greater than 9 is equal to 1 by 6, and so 1 by 6 in decimal is about zero point 0.1 something, right? I think 0.16 or something like that. So the probability that m16 of x greater than 9 is actually turns out to be much less than p of x1 greater than 9. So seems like our intuition was fine. Right, so let's move forward to the next problem, which is problem 7.1.3. And the question says x is a uniform random variable 0 and with parameters 0 to 1, and y is equal to x square. What is the standard error of the estimate of mu y based on 50 independent samples of x? So we're given a random variable x distributed between 0 and 1, a uniform random variable, and y is equal to x square, and we have to find the standard error of the estimate of mu y based on 50 independent samples of x. So first of all, we need to know what the standard error is defined as, and the standard error is defined as basically the standard deviation of mn of x, and n over here we are given basically 50 independent samples of x, so 50 samples of y. So basically what we have is the standard error is equal to the standard deviation of mn of y, which is equal to root of variance of mn of y, and the variance of mn of y will be basically equal to the variance of y divided by n, and n over here we know is equal to 50. So we know about x that it is a uniform random variable distributed between 0 to 1. So we can now want to find basically the expectation and variance of y. So y is equal to x square. So e of y is equal to e of x square, and so that will be equal to basically x square dx integrated over 0 to 1, and that will basically give us the value 1 by 3, and e of y square will be, so basically the mean of y is 1 over 3, and e of y square will be equal to e of x raised to the power 4, which will be x raised to the power 4 dx integrated over 0 to 1, and that will give us 1 over 5. And so we have the variance of y, which is equal to e of y square minus e of y whole square, which will be equal to 1 by 5 minus 1 by 9, which is equal to 4 by 45. And so we basically have variance of mn of y is equal to 4 by 45 into n. So which is basically equal to variance of y divided by n, and the standard deviation or the standard error is basically the square root of this. So basically standard error E of n is equal to root over 4 by 45n, and n is basically 50 over here. Right, so let's move forward with the next problem, which is problem 7.1.4, and the question says let x1, x2 so on denote a sequence of independent samples of a random variable x with variance of x. We define a new random sequence y1, y2 as y1 is equal to x1 minus x2 and yn is equal to x of 2n minus 1 minus x of 2n. So basically y2 is equal to x3 minus x4, and y3 is equal to x5 minus x6, and so on and so forth. And we basically have to find what is the expected value of yn, what is the variance of yn, and what are the mean and variance of mn of y, or the sample mean of y. So I think the first part is quite easy. We have the formula for yn, which is equal to x of 2n minus 1 plus minus of x of 2n, and we have to find expected value of yn. So this will be equal to expected value of x of 2n minus 1 plus minus of x of 2n. Now since these are independent and identically distributed, we can take them apart, and this will be equal to e of x of 2n minus 1 plus e of minus x of 2n, and e of minus x is simply equal to minus of ex, and both of these have the same mean, so this becomes e of x minus e of x, which is equal to 0. And similarly for the variance, we just have to use the general formula for yn. So variance of yn will be equal to the variance of x of 2n minus 1 minus x of 2n, and again since these are independent, we can split apart the two terms, so that will be equal to variance of x of 2n minus 1 plus variance of minus x 2n, and since basically variance of minus x is also equal to variance of x, so this comes out to be 2 times variance of x. And the third part says what are the mean and variance of mn of y. So mn of y is basically the weighted sum of yns, right? So y1 plus y2 till yn divided by n, and we know from the properties of sample mean that the expected value of mn of y will be the same as the expected value of y, or the expected value of yn, which will be equal to 0, and the variance of mn of y will be equal to excuse me, will be equal to the variance of yn divided by n, and variance of yn we found out to be equal to 2 times variance of x. So basically what we get is that the variance of mn of y is equal to 2 times variance of x divided by n.